let's consider the F-test, which is another famous test statistic in the old school regression literature. So the idea is simple. We have multiple regression, and our assumption, we are going to test that all the coefficients are zero, right? Except for intercept. So we are assuming that all the variables are demeaned, so we are ignoring the intercept. So it means that if the null hypothesis is true, that means your regression is useless, right? Basically, there is no prediction power, okay? So then think about unrestricted model. Unrestricted model is pretty straightforward. It's just OLS, right? Like without any hypothesis utilized in the regression, we are just minimizing the least squares. But restricted model, if you think about the restricted model, all the beta are zero, right? K observations are all zero. And then in this case, there is no estimation because already you are fixing all the unknowns equal to zero, right? Therefore, it is super simple, all right? So the restricted model is so obvious. Now then let's go back to the unrestricted model. So beta un is the minimizer of the least squares problem. Okay, so this is u. And then residual sum of squares. Remember, you may remember the residual sum of squares was defined as literally squared residuals sum, right? That is defined as, excuse me again, yi minus xi transpose beta hat squared. Okay, this is going to be the residual sum of squares. In our example, we are going to think about unrestricted models RSS. Then we will utilize beta unrestricted estimator. On the other hand, if you think about the restricted model, its residual is just y. There is no coefficient. And at the same time, think about this, y is xi transpose beta 0 plus u. But all the beta 0 is 0, right? So this goes away. So it will be more convenient to just define the RSSR as u squared, right? So y itself is the error term. Everything is just an error, okay? So we will study the minus the difference between these two, okay? So think about this. You may understand the restricted model as the minimization problem subject to beta equals to 0, right? So the restricted model is a constrained minimization. In that sense, if you observe that RSSU is L hat n u beta hat un, so this is minimized criterion function for the unrestricted model, and also RSSR is, so even though we did not write it, but let's imagine there is another minimized criterion function. This is minimized criterion function with constraint h0, okay? So then in our case we are minimizing, so then you may compare which would be smaller. Obviously unrestricted minimization will be smaller than the restricted minimization, because when you do not restrict the minimization problem, it can go deeper, right? So it will be minimizing the function better. But in this restricted minimization problem, you have additional constraint. So that will prevent you from achieving the best minimum, right? So because of the constraint, the restricted minimum cannot become the optimal minimum, right? Possibly. So this is the thing. So that means if the difference is large, that means the difference implies something is wrong. Something is wrong. If the restriction was true, then technically the unrestricted model and the restricted model should be similar to each other. So the difference should be small enough, right? So what I wanted to say here is if the difference is difference will be close to 0 if H0 is true, right? But the difference will be much larger than 0 if H0 is wrong. This is intuition, right? We'd like to show, especially we'd like to show the distribution of this guy. It should be close to 0, but how close, what is the distribution of the difference? That's what we are going to do. Okay, so let's see. Unrestricted model, RSS unrestricted model was yi minus xi transpose beta hat un squared. Okay, I am going to rewrite y as xi transpose beta 0 plus ui minus xi transpose beta hat un squared. That can be written as this times like ui plus, minus xi transpose beta hat nu minus beta 0 and squared. So that also implies summation ui then minus 2 times summation ui xi prime times beta hat nu minus beta 0 plus beta hat un minus beta 0 transpose summation xi transpose beta hat un minus beta 0. Okay, so we are expanding the square and then we get this. On the other hand, RSS restricted will be simply ui. So that means RSSU minus RSSR. Let me call this delta. Later, I will define it later. The difference is simply minus 2 times summation ui xi transpose beta hat minus beta 0 plus beta hat minus beta 0 transpose summation xi transpose beta hat minus beta 0. Of course, beta hat is always unrestricted estimator. Okay, and I'm going to define, now let's define delta n to be 1 over n times RSSU minus RSSR. Then what we get here is minus 2 times sample average of ui xi transpose times beta hat minus beta 0 plus beta hat minus beta 0 transpose sample average of xi transpose beta hat minus beta 0. I'm going to show, then you can easily see that first, this guy is going to be minus 2 times. It will be expectation ui xi transpose plus small error. So this will converge to this guy. So the error is small p1, beta hat minus beta 0, plus beta hat minus beta 0 transpose. This will be expectation xx transpose plus small p1, right? Beta hat minus beta 0. We get this. The reason why I'm doing this is because the reason why I'm multiplying 1 over n is because first we are going to ignore that. So we would like to have those two terms converge to something. So and the first term will go away. And of course the smaller terms will be ignorable. So in the end, it looks like delta n was beta n u n minus beta 0 transpose expectation of x transpose beta hat u n minus beta 0 transpose. No transpose plus small op1, but it is ignorable. So this is what we got. Okay. And now let's remember this reminds me of the chi-square thing. So if x, like say k by 1 matrix x follows normal distribution 0 and omega, then x transpose omega inverse x follows chi-square rank of omega. You may remember this, okay? Then we have pretty similar form, something transpose something or matrix times the same thing again, okay? And furthermore, what's interesting here is we know the distribution of asymptotic distribution of the unrestricted estimator. Unrestricted estimator is just an OLS, so V is expectation x transpose inverse times expectation ui squared x transpose times expectation x transpose inverse. But in particular, in our example, we have to have sigma squared, like a homoscedasticity assumption, expectation ui squared given x is always sigma squared. So using this, we may rewrite this as transpose inverse, right? So this is the variance under homoscedasticity. Therefore, so let's think about the structure. We have normal distribution. So let's do the quadratic form. Let's think about its quadratic form. So this transpose, and here we have the variance inverse times the vector again. This will converge to chi-square. Here it will be k. So because this will be rank k, right? I mean, rank of V will be k by the full rank assumption, right? So then now let's compare delta to this guy, right? If you look at this carefully, it is n times 1 over sigma square times delta n, right? If you multiply this much, then it will converge to chi-square k. So and remember, delta n was RSSU minus RSSR divided by n. So you calculate this. This is just the residuals after OLS, right? And then what remains here is I'd like to calculate sigma squared. If you estimate sigma squared is defined as, this, or simply you can just write it this way, right? This is the variance of u. And how do we estimate that? We are going to estimate this as ui hat squared. So by the way, you may multiply, say, 1 over n minus k. That is also fine, but for simplicity, let's just think about n, right? Anyhow, it will converge correctly to sigma squared. So we are going to calculate the variance in this way. What is the residual? There are two possible residuals from the unrestricted model or from the restricted model. But usually in this case, in hypothesis testing, we are going to use the unrestricted model, right? If you use unrestricted model, we are going to define the residual as this. So this residual is and think about restricted model, and this is correct only if H0 is true. Okay, this is true only when H0 is true, but this is always true, always correct, right? So the unrestricted model does not utilize the hypothesis. So regardless of the hypothesis, the unrestricted model is true. So we will take this approach. Right? That is a standard in hypothesis testing. All right. Then we are going to calculate yi minus xi transpose beta hat un squared. By the way, we have defined it already. It is RSSU. This is exactly the residual sum of squares from the unrestricted model. Okay, so the sigma squared also depends on RSS. Okay, now then, let's go back to this guy, right? What we have seen, what we derived earlier is that, like say sigma hat squared in the denominator times n times delta n will converge to chi-square k, right? But the left-hand side is n times like delta n is 1 over n times RSSU minus RSSR divided by in the denominator we have 1 over n times RSSU. Okay, so if you cancel them out, it will become n times RSSU minus RSSR divided by RSSU. This is the chi-square distribution. So as I said, this will be close to 0 if H0 is right. And it will be different if H0 is not wrong, H0 wrong, right? So that is our idea. Then how can we define the critical value? It's easy. Think about chi-square distribution, and you are going to find a critical value. So you are going to reject if let's define this as f, right? So if f is greater than a certain critical value c, such that probability chi-square k greater than c is only alpha probability, right? So this probability is alpha, right? So that means on average, even if the null hypothesis is true, your RSS will be distributed like this. But if you're unfortunate by randomness, sometimes it may look very different from 0. So that can happen with alpha probability, right? So so that means C is 1 minus alpha quantile of chi-square k distribution, okay? One more thing, by the way. So we defined the test statistic n times RSS U minus RSS R divided by RSS U converges to chi-square k, okay? By the way, the reason why the degree of freedom is k is because we are assuming that all k number of different restrictions are imposed by the null hypothesis, right? So that's why k is there. But in the undergraduate econometrics textbook, it would look like this: RSSU minus RSSR divided by k times RSSU, right? So then it will be F distribution with k and n minus k, okay? So if U was normal distribution. Right? This is old school F distribution, F statistic. Okay, and like final comment. What happens if you have n minus k in here? That does not matter. That will affect n minus k here. Still, this will be cancelled out, and you will have n minus k instead here. Okay, so you are going to have n minus k, but as you know, like n minus k over n is converging to 1. So in the end, the ratio is nearly 1, right? So anyhow, we are going to use the limit as an approximation. So it does not matter if n is large enough, n minus k over n is 1, okay? So it doesn't matter